We divide it through by p, we multiply it by x squared. Yes?
What is the, oh, never mind, yes.
Okay. And the point of this being a regular singularity was that in that case, these bracketed terms turned into analytic functions, right? In that case, these guys were analytic functions. If these were constants, then we would be back in the case of the Euler equations. But if our singularity is not that bad, then instead of constants here, we have analytic functions. And so we would get x squared by double prime plus x, and then some power series, p sub n, x to the n, y prime, and then some other power series here, q sub n, x to the n, y equals 0, y from n equals 0 to infinity, x from 0 to infinity. And if we take this thing, and if we take this q over p times x, and let the x go to 0, then we would get a constant term of the analytic function. Similarly, if we take this r over p times x squared, and let x tend to 0, then we would get the constant term here, right? And remember, so that would give us what we call the associated Euler equation. Associated Euler equation, right, was x squared y double prime plus p naught x plus p naught equals 0, right? And that thing, that guy had an indicial equation r times r minus 1 plus p naught r plus p naught equals 0. Okay, these are sort of things that pop out. Okay, and then what happened was that Frobenius, this theorem of Frobenius said that that there exists is solution of the form x to the r times a sub n x to the n, right, equals 0 to infinity, where r is some root of the initial equation. R is a root of the initial equation. So this is you know, this is not something we explain. We're just saying Frobenius says that this is going to happen. Apparently, it's pretty complicated. I've never looked at it. You know, maybe somebody should look it up and see what okay. So for those of you who weren't here on the Friday before break, much of that class was spent taking this thing and putting it into the equation, putting it into this equation, and seeing what happens. Okay, so we took that thing, right? We say, well, let y be this expression, and then differentiate it once, differentiate it twice, put it back into star, and see what is forced about the coefficients. What information do you get about the coefficients? It's just like solving things with the series as we did before, right? You differentiate once, twice, plug it in, see what's forced about the coefficients. Okay, but it turned out to be a bit more complicated. So substituting into star, we got that we got the following. That we would get a naught fr x to the r, and this thing was f of r. And here we define as a function, we define this to be f of r. And so we ended up with this plus summation n from 1 to infinity f of r plus n, a sub n, plus summation k equals 0 to n minus 1, a sub k, r plus k, p sub n minus k, plus q sub n minus k, r x to the r plus n equals 0. So you missed the Friday before break. Maybe you should feel happy. We spent most of it. We spent a lot of it getting this thing. And here, this is what it was. Okay. And so when you look at it, and by the identity theorem, we know that. Excuse me. In that case, one f of r has to be 0, right? We know that all the coefficients of these guys have to be 0, right? So particularly, we know the coefficient of this has to be 0, and we're assuming that a naught is 1 usually. A naught is some constant, some non-zero constant. So f of r has to be 0. Right? In other words, r has to be a root of the initial equation. R has to be a root of the initial equation. And then the second thing is that each of these terms in the bracket, in the curly brackets, has to be equal to 0. Right? So we see that curly bracket equals 0. In other words, a sub n is -1 over f of r plus n times summation k from 0 to n minus 1, a sub k, blah, blah, blah. max is 0, that means that a sub n is equal to minus this over f of r plus n. Okay, and so the thing to notice here, as we said last time, is that look, this says that the a sub n is expressible in terms of the a sub 0 to a sub n minus 1, right? It's some function of the guys who precede it. A sub n you can calculate from the previous guys, right? As long as f of r plus n is not 0. Okay, so you can calculate it in terms of the previous guys, but if f of r plus n is 0, then you're in trouble. Okay, so two sort of separate problems. One, you can calculate this guy in terms of the previous guys. Two, look what happens if f of r plus n is 0, then you're in trouble. Okay, and so this actually makes itself forcefully apparent in the theory, where it turns out that so if R1 and R2, the roots of f are equal to 0, the roots of the indicial equation differ by an integer, then there's trouble. Okay, or at least there's some complication. Okay. Okay, so let me say it this way. If the two roots, suppose the two roots differ by an integer, and you take the larger of the two. Okay, you take the larger of the two. Then whenever you have r plus n, you take the larger of the two as your r. Then whenever you have r plus n, you're never going to run into the other root, right? Right, because this is the larger. Let's say r2 is the larger. R2 plus anything, well, you're not going to run into r1 again, right? But if you start with the lower root, r1, and eventually, you're going to add something onto it, and you're going to end up with r2, and that will stop you from calculating your coefficients, right? You just can't go any further, right? So, however, you notice that as long as you take the bigger one, you're not going to have any trouble, right? As long as you take the bigger one, well, your coefficients can be calculated in terms of the previous coefficients, right? So you're always going to get a solution of this form. Whether or not you get two solutions of this form really depends on the roots. Okay, if you get guys that differ by an integer, well then no. If you get a double root, well then no. You actually will do something for that case today. Yeah.
So that means that n is always positive in this?
Yeah, n is from 1 to infinity. So there are sort of cases that this theory breaks into. So we've got three cases. R1 not being R equal to R2, and R1 minus R2 not an integer. That's sort of like the best case, right? If they don't differ by an integer, you can use both of them, and you're never going to have any trouble calculating the coefficients in terms of the previous coefficients. So the best case, easiest case. 2, R1 not equal to R2, but R1 minus 2 being an integer, right? So this is not so good. Just one can take the larger root only. Okay. And then there's the third case where R1 equals R2, and then in that case you've got only one. You can certainly use that one, but there's nobody else that can so you have to make it a second time in a way that we've done before. So, like, if, for example, your indicial equation had 0 and -1 as roots, right? Then you know something, right? You know that one of your solutions is going to be you can get a solution by using the upper root, right? You can get a solution by using the upper root. If it has these guys as roots, then you know that one solution will be of the form just summation a sub n x to the n. You'll have the power, something that looks like a power series, right? Because you'll have the x to the r term, but it's x to the 0. And then the second term, we don't, at least at this point, we don't know how to get the second solution.
And that 0 is because 0 is greater than -1?
Yeah. So you know that if you start from the upper root, you're okay. It's going to work out. Okay, everyone all right? Okay, so this is where we are. What we're going to do right now is the case of repeated roots. You can see that it's pretty similar to the case of repeated roots for the Euler equations. So let's do the case of repeated roots. So in that case, your indicial equation looks like r minus r minus 0. And you also know already we have one solution. In one solution, y1 is, say, x to the r1 times summation a sub n x to the n to the 1. So sometimes they'll assume that the constant is 1. They'll just assume that the first constant is 1. Okay, so we know we have one solution and we want to get a second solution. As usual, we could use the method of reduction of order. Right? We could take our one solution and then hit it with some function and plug it in and figure out the equation for the function that we're multiplying by. But we're going to play basically the same game that we played last time with the changing the order of the differentiation and getting a log term out of it. Do you remember that? Right. So here's the idea. So think we have a differential operator L, right? And this L operator, right, takes in a sub n x to the r plus n plus r, right? This is the thing that applies the left side of the equation to it, right? And then what comes out is the thing that we wrote over there. A sub a naught f of r x to the r plus n to 1 infinity f of r plus n a sub n plus summation a sub a over blah x to the r plus n. Okay, so the trick is to think of r as the variable, right? To think of r as arbitrary r. Okay, so what we were doing before, we were saying, well, we're only going to take r to be roots of the indicial equation, right? Because we wanted this term to vanish. Okay, suppose we don't care if this term vanishes or not. Okay, we're going to let r be anything. Okay, so this term we give up on. We're gonna let it stay still. Okay, okay. But then for an arbitrary r, you see something that we can still solve for the a sub n, right? A sub n can still be solved for, right? A sub n, it will be dependent on our r, right? It will be -1 over f of r plus n summation a sub k blah blah blah, right? But we can still solve for it, right? As long as we don't run into the into one of the roots. Okay. But these roots, there are only two roots, right? There are only two roots. So basically, like 100% of the time, or a very large percent of the time, your r is going to work out. Right? If you just choose a random r, basically it's going to work. Right? Unless you're so unlucky as to choose an r that differs but from one of the roots by some integer. Okay, but basically, there's only those two guys there in your whole space. Okay. So even with an arbitrary r, it's still possible to solve for the coefficients. Does that make sense? Anyone confused by that? Okay. You just use this thing, right? And the a sub n's are expressed in terms of the previous guys. So you can solve for them.
So you're saying as an arbitrary r, not if we have repeated roots, we're just not paying attention to it, not using r1 and
not using R1 or R2.
R2.
Yeah. In fact, you're staying away from the roots. You're saying let's let R vary. Okay. Let R be whatever it is. Okay. One can still solve for a sub n in such a way that a sub n equals this thing. That is, in such a way that this thing becomes 0. Right? You can solve for a sub n's of r, right? So, the point what I'm trying to say is that one can find a sub n of r so that L of a sub n r x to the n plus r equals only the first term, a sub r, a not f r. And then all these other guys will vanish, right? Because you've created these guys so that these terms do vanish, so that these coefficients vanish. Right? You've solved for a sub n so that a sub n equals, if you multiply it by s of r plus n, you get this thing, and you get minus this thing, and you get plus this thing. For that cancel. Okay. So, so what we get here is a naught, and f in this case is r minus r1 squared, right? Because we've got a repeated root. Right? And we play the same trick as before. Right? We differentiate, we take the partial derivative of both sides with respect to r. So here we get a naught times r minus r1 squared, x squared natural log x, plus 2 r minus r1 x to the r. And on the left-hand side, we play the same trick as before. We switch the order of the differentiation. And we see that if we evaluate both sides when R equals R1, so notice if we evaluate the right-hand side at R equals R1, we get 0. Right? And so we know that L of ddr of this thing evaluated at R equals R1 is 0. I'm going to go outside for a minute. I feel like you guys need to think about it. Think, digest. I'll go outside and cough. Okay. Anyone confused? Anyone confused? Anyone have questions? Any questions? Right. So we say, okay, look, we can get coefficients. As the R varies, we can still get coefficients so that L of this shifted power series, well, it doesn't equal 0, but all of these other terms, it has only the first term persists, right? All the other terms are 0, right? Right. And so we get L of this guy is that, right? And then we differentiate with respect to R and evaluate. We differentiate this thing with respect to R and evaluate at R equals R1, and we say that this vanishes, right? So that means that if we differentiate the left side, we differentiate this thing with respect to R and evaluate it at R equals R1, then L of that is equal to 0. Right? In other words, we found a second solution. Right? We found a second solution. We found something for which L of it is 0. Okay. And so the only thing we need to do is write that down. We can make it a bit more explicit if we feel like it. We didn't have to, but right. You say, well, this thing x ddr x to the r summation a sub n r to the x to the n, right, evaluated at r equals r1. It's the same thing as, well, the first guy's derivative times the second guy. Right, plus the first guy times the second guy's derivative. Equals 0, and this is going to equals 1. And at time r1. So this is our second solution. I'm just evaluating the thing in the parentheses here. So the second solution the function, right? These a sub n's are functions of R, right? Yeah. Yeah, you're not going to like it when we actually do it. Because you have to figure out a sub n as a function of R, and then differentiate it. You have to figure out these guys as functions of R. Right, they will depend on R. You'll see when you get it. It's not going to be fun. Yeah.
In the other chapters, the a sub n have just been constant.
That's right.
Okay,
That's
so
right.
this is a new.
Yeah, this is something different. Right, because remember the recurrence relation depended on R, right? It was 1 over f of n plus R, right? A sub n turned out to be -1 over f of n plus R, blah, and these the previous guys also depended on R, right? So everything depends on R, and will differentiate with respect to R to figure out these coefficients.
Did that like turn out to be that way, or did we say we want to find a sub n such that it is that so that everything else but the 0 cancels?
Answer is yes to both of your questions. It turned out that way because we demand that.
Because we want
Yeah, because we
that to be
want.
satisfied.
That's right. Because we want all those infinite terms to vanish.
So we kind of impose that condition.
That's right.
And then that's okay.
Yeah. Okay. The only thing to do here is to recognize that this is R1, right? Because we evaluated it. The only thing we make one small observation is that this x to the R1 times this thing. This is our first solution. And so here's where our first solution shows up. This was our Y1, right? So we get natural log of x times our first solution plus x of R1 summation a sub R, a sub n prime of R1. So if you had done some sort of reduction of order, maybe this is how things would work out. I don't know. I think maybe it would have worked out so easily. So our second solution looks like this. Yeah. Okay.
So the second solution will always be that form?
Yeah.
Okay.
For the repeated roots. For repeated
roots.
Yeah, not for the differing by an integer case. Yeah. That case is even more complicated, and I'm not even sure I want to do it. Like I said, there was sort of a point of what's called diminishing returns, and we may be reaching that point. Yes.
So what we did before, when we found like the second solution, we found that like if x to the R1 was a solution and there were repeated roots, then the second solution is just x to the R1 times ln x.
Yeah,
That was for the case of constant coefficients.
that's right.
And now we're looking at the case of coefficients that depend on R.
Right, our coefficients, that's right. Our coefficients depend on x, we're varying on x.
Okay. Is this 5.7 still, or is it 5.8?
I'm not sure. 5% still. Okay. Is everyone all right? We'll leave this in a second. And let me just make one small comment. What we've been doing here has all been for the case x is bigger than 0. You do the same thing as before. For the case x is less than 0, it turns out to be the reflection of this, and so it turns out to be just the absolute values. So you get absolute values on the natural log and on the x. But I'm not going to do it. Okay, so this is the theory. Like I said, there's one more case, the case of differing by an integer, but I'm not sure I want to talk about it. Let's just leave it for here right now. Let's do some examples. Let's move on to 5.8, where they give a bunch of examples of this sort of these sorts of cases. All of the examples that they give in section 5.8 are from a particular class of equations called Bessel equations. Bessel equations occur in number theory, and they also occur in as I recall, and I could be lying to you here, as I recall, they occur in the analysis of the motion of a drum. When you hit the drum, like what kind of things come out of it? Bessel functions are like the natural basis for the waves of the drum. So I could be wrong, but that's what I remember. So I think we might be able to do it. So Bessel 5.8, Bessel's function. So here is the general form of the Bessel equation. X squared y double prime plus x y prime plus x squared minus v squared y is equal to 0. And the v is called the order of the Bessel equation.
Is constant or
V is a constant. Yeah, V is a constant. And so we'll do the simplest case, or one of the simplest case v equals 0. And this will be an example